So we're here at the SID Display Week, and hi, so who are you?
I'm Elise Alkafaji. I'm the marketing manager for NovaCentrix. Today we're displaying our new PulseForge Invent system. It's a highly configurable photonic curing system for R&D and academic budgets.
So this is a new product?
Yes, this is our newest tool. The base configuration starts at 59K. As I mentioned before, it's highly configurable, so you can add additional lamp drivers to increase the power of the tool for different kinds of material processing.
It's like a rack down here?
Yes.
So what kind of things do you put in there?
So each one of these are the lamp drivers. The base configuration comes with one lamp driver system.
And how does it compare with the other products you have shown before?
Sure, so it's actually very similar to the PulseForge 1200 and 1300, but it starts out at, I would say, the PulseForge 1200 level. So if you're working with conductive silver-based inks on low-temp substrates, then a base configuration would be well-fitting for meeting those needs.
And Invent sounds like it could be suitable for students or universities or something like that?
Yeah, so we've been working with a lot of students and going out to a lot of universities and working with them to get one of these systems in their labs.
So how many did you get so far? How many there's like thousands more you should reach, or because there's lots of labs, right? And
sure.
Everybody needs to get involved with this. This is the future, right?
This is the future of print electronic applications. So I think we are close to nearing our first sale in Spain, and then we're working on a couple in the US as well, but we've visited now I think over 20 different schools, so we're working with several colleges and universities.
And the way that people do print electronics, is it basically your way, or there's other ways too?
So
do you cover most of the different ways people want to do this?
Yeah, so there's a lot of different things you can do with the tool more than just curing. There's also soldering. So my coworker Vahid is actually going to introduce one of the new techniques for using the tool, which we call photonic soldering.
Soldering. Usually people have a machine and they solder stuff. Is it what you're talking about?
So this is a soldering process that happens in a matter of milliseconds. We're using traditional soldering paste, but processing it on low temperature materials.
All right. Thanks. So let's see. So hi. So who are you?
Hi, I'm Vahid Akhavan. I'm one of the applications engineers at NovaCentrix. And as my colleague Elise has said, we're here at the Hitachi booth at the SID Display Week conference, and we're part of their portfolio of processes that we provide for the microelectronics and the print electronics world.
So you partner with Hitachi?
Yes, Hitachi is one of our partner organizations that we work with.
Like helping you achieve more things, do more stuff?
Right, exactly. We're trying to increase our bandwidth to get into different markets and provide capabilities that are currently lacking within the ecosystem that they have here at the conference.
So can you show how this machine is working?
Right. So the machine works very similarly to our other machines in that we have a very high power flash lamps.
Yeah.
We have a set of capacitor banks that get charged up with our power supply, and then they discharge it in a very digital format across the flash head. And that discharging process enables us to create a very high power flash of light in a very controlled fashion. And we place our samples here on the sample tray, and we'll be able to process it. There's our bread and butter still remains the printed electronics processing of silver and conductive traces on plastics or paper, but we're also getting into more advanced applications whereby we're able to do new things. Some things that come into play for the display kind of ecosystem involve we do some work on delamination, but the work that I would like to demonstrate today is soldering. And the process of soldering is very similar to what you described earlier, in that we have the ability to
Yeah.
So we have the ability to go ahead and use a little soldering iron to solder, but really that's not feasible when you want to do something on plastic, and that's not feasible when you want to do it in a very high throughput environment. So what we have here, we have a plastic sheet, right? So this is a PN substrate, and we have actually screen printed silver traces on top of this. So you can see the silver traces going across the path. And what we have here, we have stencil printed solder paste, and that's similar to the solder wire you get. This is SAG 304, which is a very standard lead-free solder that is used. And then we have pick and placed LEDs onto this format. So as you can see, these small bumps are LEDs.
A whole bunch of LEDs, you just put them on.
Right, there's a whole bunch of LEDs and you put them on, and that's actually the limiting factor on the processing rate. We put those on, and then through one flash of light, we're able to heat up both the component and the solder, and reflow the solder so that it actually attaches the component to that circuit.
But is it to put all these little lights on there? You do it manually, or
It's a pick and place machine.
There's another machine.
Yeah, so the pick and place machine takes, so these components come commercially available, and the pick and place machine just takes one component and we tell it where it needs to sit. And once you program the machine, it can do maybe 60 components a minute, so one component a second, and then it can place it wherever we tell it to place.
And then you put it in your machine to make it
Right, and then
fixed.
we put it into our machine and we flash it, and it actually heats up the component and the solder paste and reflows the solder paste, similar to that little iron that reflows the solder paste, enabling us to actually attach the component to the circuit.
Is this something you've been doing for a long time, or is new? Or?
This is a new application for us. The photonic soldering application, we started it late last year. We are still expanding upon it and our ability to do it. We think it fits very well with the display ecosystem, because in the display ecosystem, people are starting to move away from LCDs and OLEDs into actually LED-based displays, where you have actually each pixel is a combination of red, green, and blue small LED package that needs to be soldered in a matrix together, and then that enables us to make a big display.
So you're going to be part of the micro LED world?
We are hoping to be part of micro LED world. We think that this kind of capability can be miniaturized to enable us to process micro LED displays.
All right. And so what else is next?
So let me light this up for you so you can see it actually in action.
Nice. So there's no mistakes in it. It's just,
There's no
it's just
mistakes.
reliable.
Yes, exactly.
Right.
So this enables us to really do quite a lot of work related to that. The other application that we are targeting at the show is called delamination, where we use our high power units to delaminate polyimide substrate from the carrier glass. This is currently done in the OLED manufacturing designs with lasers, where they take laser from behind it. Once the OLED material is built, they take laser and they shine laser at the interface between the glass substrate, the polyimide substrate and the glass carrier. And that releases that layer from the carrier. And then you have a freestanding, flexible display material. One of our aims with doing it with our tool is that there are a couple of drawbacks when you use laser. One of the big ones being speed. You have a very low speed because you have a very small illumination area that you have to raster in a very continuous format to actually delaminate the display from a glass. And that creates a very expensive delamination process. The other issue is that you have a very low yield, because if you, for example, have a defect in your polyimide material, the defect acts as a lens it can actually burn out that part of your OLED material. And so you get a defect in your device, and then you have to cut it out. The other issue is that when you're using laser, you get an ashing process where you have some decomposed polyimide remaining in behind your release layer. With this process, what we do, we take the carrier glass and we deposit the absorber. We deposit a very thin metallic layer on top of that enables us to take advantage of the absorbance of that metallic layer and heat up the interface between the deposit polyimide and the metallic layer. And then once we cure that, we can easily release that as well. Release the polyimide layer from the tungsten absorber layer. That process has some advantages. One is that because of our high illumination area, we can process at much faster rates. We can process up to 100 meters per minute if necessary. The other advantage is that the light never actually shines on the polyimide substrate, so that what happens is that you don't get any ashing, you don't have an issue with defects, and so as a result of both those issues, your yield could be higher in the process.
So there's a lot of people in the industry interested in those solutions you have?
We have had quite a lot of interest, yes. We are working with several partners very closely to be able to bring those applications to realization.